I'm going to be using the AmeriKit AK100 to learn how to solder with electronic series. So we're going to learn to solder a kit and build a flashing European siren. We can begin our career in electronics now. We're going to build this kit and learn basic soldering techniques. We'll learn how to solder on a state-of-the-art PCB printed circuit board. All electronic components are supplied, including soldering iron and wiring cutters. So we have everything in this kit right here. We're going to build a European siren with flashing lights and learn how the circuit works. The lesson manual is underneath here, and it's also included. So this European siren with flashing lights can be used as an intruder alarm, a bicycle siren, or just plain attention getter. If we've never soldered before or just want to sharpen our skills, this learn by doing module is going to make soldering fun, so this looks pretty cool. We have our PCB printed circuit board right here, and we're going to be able to solder through these small holes and everything on here, and then hopefully connect things. We're going to become an expert in soldering. No previous soldering knowledge is required. We can gain a practical knowledge of our electronics, build a flashing European siren, complete with all components including soldering iron and wire cutters, and a lesson manual and self-test included. So we have all this inside of here. We have our soldering practice kit. We have our wire cutters, this nicely included soldering gun. We also have our PCB where we can practice soldering along here, but not along here. And then the rest of our components as well as solder here as well. So we're going to use all of this to build this kit with the instructions. And now we're going to go over the instructions and practice parts for this. Looking at our manual, we have model SP1A, we have a QR code as well that we can scan. It's an assembly and instruction manual by Elenco. So this is the soldering practice kit. On this first page, we have our parts list. So we have our resistors and the color code for them. We have our capacitors as well. We have two kinds. We have disc caps and electrolytic capacitors. We have some semiconductors as well with descriptions. We have a transistor, NPN. We have a integrated circuit timer and a LED, which is our light emitting diode. To the left, we have our quantity, our symbols and values. And that's the same for the resistors up there as well. We have some miscellaneous as well, like a PC board, solder wick, battery snap, speaker, wire, and a solder tube, which is lead free. That's nice. And then we also have part numbers here. So if we need replacements or anything, we can look at that. Something really important is to identify our values for both capacitors and resistors. We can use the following information as a guide in properly identifying the values of our resistors. So we have 3 bands and then a 4th band. The last band, the 4th one, is tolerance. So this is like the delta of how accurate it is. Bands 1 and 2 are simply digits. So they'll be from 0 to 9. That's what these will be. And then we have a multiplier. So if we have like a red and a red for bands 1 and 2, we would have 2, 2, and then this multiplier would be multiplying it by whatever this is. So if it's orange, if we have red, red, and let's just say red, we would have 2,200, and that would be our resistance. So basically 2.2 kilo ohms of resistance for that. Next, we have identifying our capacitor values. And when we identify our capacitor values, capacitors will be identified by their capacitance value, which is picofarads, nanofarads, or microfarads. So farads is the main unit, and then these are just the conversion for abbreviating it to smaller or larger. Most capacitors will have their actual value printed on them. Some capacitors may have their value printed in the following manner. Most capacitors, which are electrolytic, are like this, and they have a actual value on them. These ones are going to have like this little code, how we have the resistors right there. The maximum operating voltage may also be printed on the capacitor as well. So we can see for this type, we have our maximum working voltage at the bottom. We have our first digit, second digit, and a multiplier. This K is going to be our tolerance here. Electrolytic capacitors have a positive and negative electrode. That's going to be these here. The negative lead is indicated on the package by a stripe with a minus sign, possibly arrowheads. Also, the negative lead on a radial electrolytic is shorter than our positive one. If the capacitor is connected with incorrect polarity, which is basically the way the current voltage power flows through it, it can heat up and either leak or explode. So we always want to make sure that this is in the correct direction. For this one, it's going to be just like our resistors. We have the number and we have the multiplier by. So, and we have an example of this right here. We also have our tolerance indicators, M, K, and J. The letter R may be used at times to signify a decimal point, as in 3R3, which would be like 3.3. We have metric units and conversions, and this is very simple, very standard, and we've looked at this a lot in videos doing problems. Next, we have a resistor exercise page. This is pretty simple, so I'm not going to go too much into it, but it's good if you've never looked at resistors before. You can always look this up though, so it's not really something you necessarily memorize. However, you do want to know how the actual wording of this is. If you're given these colors, you should be able to decipher the resistance and tolerance of it. Next, we have an introduction. Almost every electronic device today has a printed circuit board, PCB. Whether we are assembling a PC board or repairing it, we must understand the basics of working with these boards. Good soldering requires practice and an understanding of soldering principles. The Solder Practice Project will help us achieve good soldering techniques, help us become familiar with a variety of electronic components, and provide us with dynamic results. If the circuit has been assembled and soldered properly, two LEDs will alternatively flash and the speaker will produce a wailing sound. Hopefully not too loud, but we'll see. We have some safety precautions. Like all electrical devices, the soldering station must be handled with care. The soldering iron and tip can reach high temperatures, and these simple safety rules should be followed. First, we keep children out of reach of the soldering station. To protect our eyes, we're going to use safety goggles during all phases of constructions. We can keep flammable material away from the soldering iron. The safety goggles aren't included, but they can be picked up pretty much anywhere. You do want to make sure you get a nice pair that really protects your eyes though. Do not cool the iron by dipping it in any liquid or water, that's really bad. Always assume that the tip is hot to avoid burns, so never touch the tip even when it's cool. We are going to work in an area that's well ventilated, so I have a HEPA filter, window open, door open, and we want just some filtration so we're not breathing in all of that. Be careful that the hot soldering iron tip or the barrel of the iron does not come in contact with any electrical cord. It can easily burn through the rubber insulation and possibly cause some short or a fire, or anything like that. Next it says, do not hold solder in your mouth. Wash your hands thoroughly after handling solder, because you don't want that getting anywhere and you don't want any residue. We're going to locate the soldering iron in an area where you do not have to go around and reach for it. So basically, while we're working on this project, we want it to be ready right in front of us. Next is solder. Solder is a fusible material ideal for forming a metallic joint between two metals. Lead solder is comprised of tin and lead, identified by the ratio of tin to lead. The most common cases are 6337, 1647. The first number indicates the amount of tin, the next is the amount of lead. It has a melting temperature around 360 to 370 degrees, so that can tell you how hot this iron can get. For health reasons, lead-free solder is widely used and included in this kit. Lead-free solders contain high percentages of tin, almost always over 94%. The lead-free solder in this kit contains 99.3% tin, 0.5% copper, and has a rosin flux core. The melting point of lead-free solder is about 40 degrees Fahrenheit, higher than leaded solder. So it takes longer to melt, higher temperature, but it is healthier. Tin is a corrosive and active metal, and when it mixes with iron, the protective layer of the tip, an intermetallic compound is formed that wears away more quickly than the iron would either by itself or when using with our lead solder. When using lead-free solders, it's important that tips are properly maintained, otherwise tip life will be reduced significantly. Tips should be cleaned frequently to remove oxidation before it becomes impossible to remove. The iron should be turned off if it is not used for extended periods of time. Next we have our flux. Most solder contains flux in the hollow core of the solder, allowing it to be applied automatically when you heat up the solder. The flux will remove any oxide film on the metals soldered, creating a good metal-to-metal contact. This is called wetting the metal. There are three types of solder fluxes: chloride, organic, and rosin. In the electronics industry, only the rosin type is used. Rosin flux comes in two types, pure and active. The most reliable is the pure type, since it doesn't cause dendrites between tracks on the PC boards as the active type does. Due to the highly corrosive and moisture attracting characteristics of the chloride, and organic type fluxes, they should not be used in electronics. Now we have surface preparation. In order for the solder to adhere to the connection, the metals must be clean and free of non-metallic metals. In order for the solder to adhere to the connection, the metals must be clean and free from non-metallic materials. Flux in the solder can remove oxides from metal, but not other materials like dirt or grease. To remove these, we should use a small steel brush and a cloth. We have a mechanical connection. When all the surfaces are clean, the metals should have a solid mechanical connection. Wires should be tightly wrapped around each other or to the terminal. This will eliminate large gaps and create weak solder joints. Solder should not be used as a mechanical connection. So we would want it kind of hooked like this as it's shown. That way there is a strong connection, and then the solder is basically just what connects it, not what holds it together. Next we have types of soldering devices. A number of different types of soldering devices, such as irons, guns, and stations, are available today. Irons are used for light to medium work, and guns are used for medium to heavy duty work. We're using our soldering iron here. For working on PC boards, iron range from 15 to 40 watts are suitable, or a station with a range of 15 to 40 watts. If we use an iron with a bigger wattage rating than 40 watts, we may damage the copper tracks on a PC board. We don't want to get too hot. The higher wattage irons are best suited for more heavy duty electrical jobs. Soldering tips. The tip is the very important part of the iron. The material that the tip is made from is an essential factor. The soldering iron tip contains 4 different metals as shown in our figure here. The core consists of copper because of its high thermal conductivity. Since the copper is a soft material, it's plated with iron to maintain its shape so it doesn't bend. Chrome plating is used on the area where no soldering takes place to prevent oxidation, so everywhere except for the very tip. The tip is plated with tin so that it can be cleaned very easily. And we can see the slight difference in color. There is a slight difference in the material of our soldering iron. So you can see it gets a little bit darker at the tip. And that's because of the different kind of material that it's coated in. Today, tips are manufactured in a variety of different shapes. We can see below, the chisel shape is the most common. Having a choice of tip styles allows us to choose the one best suited for our soldering needs. Due to the high heat, removable tips can bond themselves to the heating element if left in place for extended periods of time. Periodic removal of the tip is therefore advised. That way you don't have it stuck on your iron, gun, or station. Next we have tip cleaning. A good clean solder tip makes soldering much easier. The tip should be tinned by lightly coating it with solder to prevent it from oxidation. The tip can become pitted, which has black spots, from normal use. It's important to clean the tip by wiping it with a wet sponge or rag, so that after it dries, we can wipe it down. For tips that need good cleaning, the tip tinner and cleaner should be used. Never use a file or abrasive material to clean the tip. And the tip tinner and cleaner is TTC1. I'm assuming that's given to us, but we can always check back later. We're never using a file or abrasive material to clean the tip. Using such methods may damage the plating and ruin the tip. Do not remove the excess solder from the tip before storing. The excess solder will prevent oxidation. So when we're done, we're going to want to leave some solder around here so that it doesn't oxidize. Now we have clean connections. Proper solder adhesion requires that the metal surface to be free of dirt and grease. The flux only removes the oxides, so a brush or rag can be used to clean the metal. There are contact cleaners and aerosol cans and other solvents that are available. Now we're going to look at desoldering. A great care should be taken when repairing or correcting a mistake on a PC board. The metal foil can be easily pulled up or broken from excessive heat. We want to use the least amount of heat as possible. We can use a desoldering tool, a bulb, wick, or a station. These tools will remove the solder, enabling us to correct the problem. We have our solder board here and soldering iron that's heating up. We're going to use the solder as well to do some solder practice on here. Before we begin to assemble and solder the components of the solder practice PC board, we will start first by practice soldering to the double pads on the edge of our PCB board. These are going to be the ones on the back right here. Apply a small amount of solder to the iron tip. This allows the heat to leave the iron and onto the foil. So we're going to place some of the solder onto the iron tip. I can smell it already starting to heat up. We're going to place the iron on the top half of the pad and then apply the solder. So we'll place the iron at the top and then put our solder on top of it. We're going to allow the solder to flow around the pad, then remove the solder and the iron and let the solder cool. The solder should be neat and smooth. So we're going to repeat step 2 on the top row of all of our pads right here. So we're just going to practice that. So for this first one, I'm going to move this aside because there's a little bit of crease in the paper, and we have it on the board like this. Placing the soldering iron down first, we can now place some of this on here. We can see it starting to melt a little bit. I'm going to grab the solder brush by my fingers and pull it out a little bit more. I'm going to actually pull this lid off so we get all the solder like this. So again, we're placing the iron on the top half of the pad and then apply the solder to the lower part of it. So we'll place this here. Solder is still a little bit hot. It's going to look like that. And that is a better solder than what I was doing. I was just wasting solder at the previous part. So now we're going to let it cool. As you can see, I might have messed up a little bit. It seems to be a little bit over onto the other pad. So good thing we have multiple pads to try this out. You don't really want to touch yourself other than like touching this, so you don't get any of the possible residue. There's little sparkles on my finger. You don't want to get that just everywhere. And make sure you're wearing safety equipment like glasses. I'm going to pull more of this out so that we can use more of it. And now I'm going to go on to the next part. So the solder is going to go on the top half, or the iron is going to go on the top half, and the solder will go just below it. And that looks okay as well. So I did a better job on the second one than the first one. Now we're going to keep going. So we'll look at the next one right here. So I'll place my iron down here, and then I'm going to apply some solder, just like that, and let it cool off. That one looks pretty good, I think, as well. We can see that the first two are touching, which I don't think is exactly what we want, because that'd probably be conductive and carry some charge straight across that. But this next one looks good. It's just on the single pad itself. So now we're going to move over to this next one. Soldering iron is going to go right here, and then our solder itself is going to go on top of it, or below it, not on top. And boom. So those two look good. I'm going to keep practicing on these other ones. Alright, so I believe I finished all of the connections. We're going to take a look at the board a little bit closer now. Looking at our board, we can see all the little solder joints that I have made. They look like this. The first one is not great. It looks like that they're touching each other, so I don't think you want that. The second one, they're not touching each other. They're not even really that close, just the camera angle. The third one is good, fourth one is good. Everything else looks pretty much good. If you touch them, that's the dry ones, it's just solid. And so this is just wetting, I think it's called. We're preparing it to solder something else on, and that is just basically preparing the board. We have some more practice parts right here. But now we're going to look back at the instructions for a little bit. I did notice that there is some blackening around the tip, and that was foretold. We've looked at that previously, so there's no issue around that. We're placing our soldering iron down, and we just want to make sure it's not above anything that can burn like plastic or paper or another wire. So we're going to repeat that. We've practiced. Now we're going to look at single pads. Now practice using these single pads, which are these down here. Use the same soldering procedures as the large double pads. Be sure there are no solder bridges between the pads. So I guess that means it was okay for the solder to be on both of these, but it should not be touching for these ones. And also, you can see my solder edges are a little bit pointy, and it says right here that you don't want them pointy. So I think I could go in with my iron and melt it down just a little bit to make it smoother. And I'll try that right now, actually. Not too much luck, still a little bit of a point to them, but I don't think that matters too much because we are going to be soldering something on top of it. We're just wetting the board here. I think they are able, if they're able to touch each other, just move it around like this. That gives it a little bit nicer, a little bit smoother. So you can see the one that I just did right here, it's smoother compared to the ones that are sticking up and pointy. So that's just something to note. The solder bridge. Solder bridges occur when solder runs between circuit paths and creates a short circuit. This is usually caused by using too much solder. Using the top row of our single pads up here, we are going to try to intentionally make a solder bridge on each section, then remove it by simply dragging our soldering iron across the solder bridge as shown. So we're going to do that here. We're going to intentionally make a mistake and then try to remove it. It's best to wipe the iron tip with a wet sponge to remove the solder. We can use our soldering wick as described in page 7. So, grabbing our board, we're going to intentionally make the mistake of soldering between these two different parts right here. So we'll place some solder right here. We'll coat that. And we'll purposely use a little bit too much right there. And then we'll do the same thing using a little bit too much right here. So these are fine by themselves, but now I'm going to use the actual little bit too much and bridge the gap between them. Now we don't want this because it's two of them connected. So what we want to do is once that dries a little bit, we can take our iron, like let's say we made a mistake, and we're going to just drag it in the middle and try to break it apart. And as you can see, that does break it apart. So now they're two totally separate parts. That's pretty good to practice on. And we only really need to do one of those because we've kind of worked it out at the top here. That's easy to just break apart, and that was just showing us how we can desolder if we make a mistake. Now we have the solder resist. The PC board is covered with solder resist over areas that are not to be soldered. This is done to reduce soldering shorts to adjacent metal runs. On the large pad, note that half the pad is covered with solder resist. We can try soldering on the cover pad and we'll find that it's nearly impossible. And that's going to be this part right here. So we can try to put some solder on it. This is just residue left over from the iron and it's not sticking. If we put it on the metal part right here, we can see it'll actually form and stick to it, whereas it won't on this one. So that's pretty neat, pretty nice defensive feature right there. You can see the difference of it actually sticking versus not sticking to the board. Note there are 3 pieces of wire included. Save 1 piece for the speaker assembly. And I believe that it's going to be referencing this blue wire right here. Taking it apart, we just have one really long wire like this, not multiple wires. We're going to be looking at tack soldering. We will make 14 tack solder connections by soldering 7 wires to the top row of the pads. We're going to cut 1.5 inch wires and strip 1/8 of the insulation off of both ends. We're going to place the iron on the wire at the top pad as shown in figure 7, which is going to be this one right here at the bottom, and we're going to allow the solder to flow around the wire. Then remove the iron and let the solder cool. We may need to add some more solder. The solder should be neat and smooth. We're going to pull the wire to make sure we have a good solder joint. We're going to bend the wire and solder it to the next pad as shown. Now solder the remaining wires to the pads. We can see I burnt my paper a little bit just from leaving this on here too long. We can see that there is a little bit of solder still left on the actual tip. And it's not focusing, but there is just some remaining right there. That's a little bit of the bulge. So now we're going to grab our board, we're going to grab our wire, and we're going to take our wire cutters that were included, and we're just going to snip a little bit off. And then we can place it in this hole right here and just pull the insulation part off. Okay, that was really hard. So I'm probably only going to do one of these because I don't have a pair of actual wire strippers. The one that came with is not amazing for it. I've really just been going in and trying to bite off any of the wire that I can to get some exposed wiring so there's no insulation on it. So what we're going to do now is we're going to take this wire and we're going to try to solder it onto here. We can try to position it so it'll hold itself in, and I can just solder it down. We're not going to use that first one. We'll use this nice one that I semi-fixed right here. So we'll take it like this, and I have some solder on my tip already. So I'm going to try to solder that into place.
It actually just got really hot on the wire itself. The insulation got really hot, so I had to let go. But I'm gonna try to place it in there. And it's melting away some of the insulation. And the wire is just a little burnt, the insulation on it. So what I'm gonna try to do is use tweezers to move it and get it into position for the next part. Put this into place like this. Still have some solder on the tip. So I'm gonna try to do that right here. You might need some more solder though. I'm going to use just a little bit more to make sure it's sturdy. And now we can let it cool off. Alright, so I pinched the wire a little bit, trying not to bend it too much because it is a little bit weak, I think. But we've got it. Cut down another wire. It's going to look like this. We have our metal part and we have the insulation. I'm going to bend it so that we can try to just easily put it on there, rest it on there, and then use the solder to hold it down. So my thought is, as long as our wires are straight, we can use the existing solder already on here to try to actually melt it down together and hold it in place, and then come in with some more solder. I'm going to do the second best one, which is probably the last one, or the second to the last one. I'll do that right now. Just in case the insulation gets hot, I'm going to hold this with tweezers. Looks like it's staying on it. Ow! I just burnt myself a little bit. I didn't touch the tip. I just touched this part right here accidentally with my finger. So I gotta watch out for that. I'm gonna add a little bit more solder onto this joint right here just to make sure it's steady and sturdy. That connection seems to be fine. Now I'm going to solder down the next part. So this is gonna go right here like this. And then I'm going to just push it in a little bit to hold it in place. That looks good, and now I'm going to bring in some more solder to hold it down. I made the mistake of melting away some of that rubber insulation again. It got kind of shiny, mostly to the right. You can see to the left, it is not as shiny. So we can see that unlike this one, if I pull on it, it wiggles on the right a little bit. So we didn't solder it down correctly. So what I'm going to try to do is just push this in a little bit more with the solder that's already on the plate, and then add some more again. Seems like I missed it and must have just hit the insulation. So I melted that down a little bit, and now I'm putting some more on there. We can see that before it dries, there's some fresh solder right on there. It's a little bit shinier than the other one. It seems to have dried. If we just tap on it, it feels pretty dry. We can now pull on it a little bit. We can see that it's not coming loose. That's good. And here we are done with this example. So that's it for our example. We could keep practicing more if we want between all of these. And now we're going to look at some more board repair and removal of excess solder. So just a summary of this. Then we can move on to the next video. That'll be in the description below the like button, where we will be actually building this entire circuit right here. Looking at PC board repair, we first have hairline cracks. The hairline crack can develop in the copper foil if the PC board is flexed. So if you have a board and you fold it down the middle, it could crack. Now that means there's going to be a crack like this, and it's going to be a hairline crack. This can be easily repaired by making a solder bridge across the two cracked foils. The solder should smoothly flow across the foil as shown in our figure 8. If the solder does not adhere to the foil, it will sit on the foil and a blob will be what it looks like, and that's in our figure 9. We can make 5 solder bridges using the second row of our single pads starting from the left side. So you can think of it now as these two broken parts, and now we have this part in the middle that we wanted to solder. So we've done this previously, like how we had this one right here, and then we drew a line to it so we could fix it because we wanted them on 2 separate parts. For this one, all we're going to be doing is the same thing. We're just putting them on 2 separate pads and pretending that's kind of like the foil, and then we're going to add another solder on top of it That way it'll combine the two together. We're not going to do that because we just did it here, but that is how that would work. Now we look at reinforcing a repair. A solder bridge repair can be reinforced using a solid wire. Now add a wire to the 5 solder bridges you just made. So what we can do is get a wire. So we're going to strip a 1/2 inch of insulation off of the end of the wire and then tin it. We're going to hold the tin wire on top of the solder bridge. We're going to place the iron on the wire while the solder melts. We're going to remove the iron while holding the wire in place against the foil. We got to make sure the wire does not move until the solder happens, that way it gets a firm hold. We're going to check for a good solder connection, cut the wire off as close to the solder joint as possible, and practice this procedure 4 more times. So we have something that it'll be like across here if we want to combine them. For wider gaps in a copper foil, a solder bridge cannot be used. So if we have something across like this, it's not going to be as easy as doing it like this. A small wire would be used to bridge the copper as shown in our figure 11. 6 bridges will be made across the 2 rows of small pads. So we would just be bridging the gap here, and we can do that and also demonstrate this as well once we have our solder on. We're going to place the iron on the top half of the pad and then apply the solder. Allow the solder to flow around the pad, then remove the solder and the iron and let the solder cool. The solder should be neat and smooth. We're going to repeat step 1 on our lower pad. Then we're going to strip 1/2 inch of insulation off one end of the wire and then tin it. Hold the wire on the top pad and place the iron on the wire. The solder is going to melt and the wire will press down into the pad, so it'll look like that. We're going to remove the iron while holding the wire in place against our foil. We need to make sure the wire does not move until the solder happens, that way we have a good connection. We're going to check a good solder connection, solder the wire to the lower pad, cut the wire off as close to the solder joint as possible. We can hold the wire down with a screwdriver and resolder the wire if we need to, and practice this procedure a few more times. So we're going to do 2 of these and then also 2 of these. We're going to pretend we have a hairline crack, and to pretend we have a hairline crack, I'll go over to this part of the board, and we need to make the underlying foil part. So we'll put some tin right here, and then we're going to do it on this part as well. Now in between them, we're going to act as if we have a hairline crack. We can see that there is a small split down the middle. We want to join them together as if we were repairing something, as if this cracked down the middle. So we can take some of the solder, put it on our gun, and join them together. Now it's going to be a little bit challenging since it doesn't inherently want to go in between, since in the middle is a solder resistance part which is on the board. So we can see that it has now been joined together. Now we're going to look at the wider gaps. This is where we're going to need to take some of this wire. We are going to have to cut it and join it together. For this, our wire shouldn't be too long since we're only going from here to here. So what we're going to want to do for our bare wire is probably cut it around this part right here and then strip it entirely. So now we have our completely exposed wiring. What we're going to do first is we're going to add some solder onto the pad. We'll start on the far right. We already have some solder on the gun, so we just need to add a little bit more and put it on this pad, and then put it on this pad. Now a bridge would not work here like we did this previous one because they're a little bit too far spaced apart. Now all we're going to do is let that dry a little bit. This is going to get a little bit hot, so what we're going to do is hold it by some tweezers. We're going to hold the wire by some tweezers, and we will start from the lower part and then go to the upper part. So placing the wire down here, we are going to remelt that solder, and we're going to hold it in place until it hardens. Once it hardens, it should not move. It looks okay. And now we are just going to do it for the top one. So positioning it right here, we can try to melt the solder so that it flows around our metal wire part. And if that doesn't work, like it doesn't seem like it is here, what we can do is always add more solder. It's not working here, so I'm going to pick up the solder and we're just going to melt some more on top of it so it flows around our wire. and it looks like it's a little bit loose on the left hand, or the bottom part. So I'm just going to melt it down a little bit so it can flow around a little bit nicer. From here, it's hardened. We can try to pull it. It's not going to come out. We can tap it, and we can see that it has a secure connection between them now. We're going to look at removing excess solder using a solder wick. Desolderizing wick is a braided wire coated with non-corrosive rosin flux. It is the simplest and safest tool for removing solder with a solder connection. When the braided wire is heated, the flux cleans and breaks up the surface tension, so the melted solder from the connection flows into the braid by capillary action. Included in this kit is a 6-inch length of solder wick. It's a desoldering braid. We're going to place the solder wick, so the kind of gold part that we're given, on one of the pads and the iron on top of it. As the solder melts, it's going to be drawn into the wick. When the iron and wick are removed, the solder should be removed. We need to repeat the process if the solder remains. If necessary, repeat the procedure until all of the unwanted solder is removed. After the excess solder has been wicked away by the desoldering braid, clip off and discard the solder saturated part of the braid. For best results, always use a fresh area of the braid for each procedure. Caution, the wick is going to get hot, so we're going to use some long needle nose pliers, which is what we have here, and we're going to hold the wick. We have our excess solder, and then we have a diagram of what this is going to look like close up. So we're going to do this here. First, we're just going to apply some solder to a pad. I already have some on the gun, so I'm just going to melt some of it down here. I'm going to want to just coat the iron, not gun, but iron a little bit in it to prevent oxidation. And now I'm going to put some on the pad itself. So placing it down here, we can get a nice heap of solder onto that pad. We can see that there is now solder on that pad in the middle, and we're going to want to remove it. So what we can do is we can open the bag, and we're going to use this braided cable. So using this braided cable, we can remove some of this solder. What we're going to do is just place it over, and then we're going to place this wick on top. It's going to get hot, so we are going to use the pliers to hold it this time. Taking this, we'll place it right on top, and we are just going to push it down. It looks like it's absorbing it. We want to make sure the iron stays on here. That way it will not melt it together. We want it to be absorbed inside of here. Just rubbing it around a little bit. We're getting a lot of it off. I did place a lot on here though, so we can just keep moving it around. So you can see a lot of it got absorbed into the wick, and a lot of it was removed from our actual PCB. And it looks a little bit dark, but that is just from the actual iron itself. All of the solder has been removed. We next look at our theory of operation. The solder practice kit consists of a circuit oscillating at 1 Hz, so 1 cycle per second. The oscillator consists of 2 transistors, which are going to be Q1 and Q2, and resistors, R1 through R11, and capacitors C1 and C2. So if we look at everything we're given, they're all labeled to us right here. These are all of the parts and components that we have. This configuration is known as a multi-vibrator circuit. The solder practice kit produces the sounds of a European siren. It consists of 2 oscillators, a 1 Hz, 1 cycle per second, and a 1500 Hz. The 1 Hz oscillator consists of 2 transistors, Q1 and Q2, and resistors R1, 2, 6, and 7, capacitors C1 and C2 as well. This configuration is our multi-vibrator circuit. When voltage is first applied to the multi-vibrator circuit, one transistor, could be Q1, will conduct faster, causing transistor Q2 to stay off. So we're going to have whichever one is faster be the one that goes to the output. Q1 will continue to conduct until it saturates. At this point, Q2 will start to conduct, causing Q1 to rapidly cut off. This process continues alternately, causing Q1 or Q2 to conduct. The output will be a square wave. The output will be a square wave. The frequency is determined by the time constants of resistors R6 and capacitor R1 and R4 and C2. 2 LED diodes are placed in the collectors of the transistors, and these are going to be right here. The LEDs will light when current is passing through them. Resistors R2, R1, and R7 determine the current passing through the LEDs. So looking at our resistors, we have R1 right here. We have our R2, and our R7 is going to be right here. so current takes the path of least resistance. Integrating circuit IC1 is the heart of the second oscillator. A 555 timer IC is used in the circuit. This IC contains many transistors and resistors on a silicon chip and thus eliminates many external parts. The frequency of the oscillator is determined by resistors R5, R9, and capacitor C4. Capacitor C3 couples the output of operations of IC1 via resistor R8. This changes the operations of our IC1 during one half of the multivibrator, causing the frequency to change from 15 Hz to 22 Hz, and that's the alternating sound. This results in a speaker output that varies constantly in pitch. The multivibrator circuit not only causes the LED to flash, but also varies the pitch at the speaker output. Note, resistors are in ohm, capacitors are in microfarads. Our solder practice kit is given here, and we have our circuit diagram here. We have the battery, we have capacitors, those are what these look at. We have resistors, we have more capacitors, and we have more over on this side as well that we're going to make, like a speaker. We also have our IC amplifier and volume control here, ground, capacitor, and more resistors. Now for construction, we have our introduction. The most important factor in assembling our solder practice kit is good soldering techniques. Using the proper soldering iron is a prime of importance. A small pencil type soldering iron of 25 watts is recommended, which is what we have here. The tip of the iron must be kept clean at all times and well tinned. Solder. For many years, leaded solder was the most common type of solder used for the electronics industry, but it's now being replaced by lead-free solder for health reasons. This kit contains lead-free solder, which contains 99.3% tin, 0.7% copper, and has a rosin flux core. Lead-free solder is different from lead solder. It has a higher melting point than lead solder, so we need higher temperatures for the solder to flow properly. Recommended tip temperature is approximately 700 degrees Fahrenheit. Higher temperatures improve solder flow but accelerate tip decay. An increase in solder time may be required to achieve good results. Soldering iron tips wear out faster since lead-free solders are more corrosive, and the higher soldering temperatures accelerate corrosion, so proper tip care is important. The solder joint finish will look slightly duller with lead-free solders. Use these procedures to increase the life for the soldering iron tip when using lead-free solder. You want to keep the iron tinned at all times. Use the correct tip size for the best heat transfer. The conical tip is the most commonly used. Turn off the iron when it's not in use or reduce temperatures setting when using a soldering station. Tip should be cleaned frequently to remove oxidation before it becomes impossible to remove. Use dry tip cleaner or a tip cleaner. If you use a sponge to clean your tip, then use distilled water. Tap water has impurities and accelerates corrosion. Safety procedures. We're always going to wear safety glasses or safety goggles to protect our eyes when working with tools or soldering iron and during all phases of testing. Be sure there's adequate ventilation when soldering. Locate soldering iron in an area where we do not have to go around it or reach over it. Keep it in a safe area away from the reach of children. Do not hold solder in the mouth. It's a toxic substance, and we need to wash hands thoroughly after handling solder. Assembling components. In all the following assembly steps, the components must be installed on the top side of the PC board unless otherwise indicated. The top legend shows where each component goes. The leads pass through the corresponding holes in the board and are soldered to the foil side. Use only rosin core solder. Do not use acid core solder. So we have good and bad soldering techniques. We're going to solder all components from the copper foil side only. So that means this back side right here. Push the component iron tip against both the lead and the circuit board foil. We have our lead, the foil, our board, and the soldering iron. Apply a small amount of solder to the iron tip. This allows the heat to leave the iron and onto the foil. Apply a small amount of solder to the iron tip. This allows the heat to leave the iron and onto the foil. Immediately apply solder to the opposite side of the connection, away from the iron. Allow the heated component in the circuit foil to melt the solder. Allow the solder to flow around the connection. Then remove the solder and the iron and let the connection cool. The solder should have flowed smoothly and lump up around the wire lead. This is what a good solder connection will look like. We have insufficient heat. The solder will not flow on the lead as shown. Insufficient solder. We want to let the solder flow over the connection until it's covered. Use just enough solder to cover the connection. If we have solder here and a gap here and our lead going through the middle, it's not going to work well. We have excessive solder. It could make the connections that you did not want to make, so That means we could have, if we have something like this too close, we can put them together when we don't want to. Solder bridges occur when solder runs between circuit paths and creates a short circuit. This is usually caused by using too much solder. To correct this, simply drag the soldering iron across the bridge as shown. We've gone over this before, and it'll break it apart. Next, we have our PC board assembly. Before beginning assembly, we want to refer to page 13 for the resistor reading exercise. It's going to familiarize us with the resistor coloring and band. We'll look at that in a second. We have basically a whole layout of what we're going to put in the board and why. We're going to go over that when we actually put everything into this board. All of this is just instructions on what to do with this board and some more PC board assembly here. Lastly, we have operation, desoldering, troubleshooting. We're not going to look over this, but it is right here. And lastly, we have our word glossary, so if anything's unfamiliar, we can just look at it through here. Now we're going to do our PC board assembly following the instructions laid out here.
Here we have our PCB, or the printed circuit board, PCB. First thing that we're going to do is have the battery terminal. So this is where we're going to power our device. I believe it's like 9 volts going into it. We're going to solder the red positive, which is the plus lead of the battery snap, to the hole marked positive on the PC board. Solder the black negative lead to the hole marked negative on the PC board, and then we're going to cut off any excess leads. You can see here that the leads are actually pretty small, so I had trouble getting them to stay in. I was able to eventually bend them back, though the only red one stayed in. And after I was able to do that, I got it to hook on, and then I was able to grab my soldering iron and then solder the red one down, and then do the same for the black one. What I could have done, and I realize this now, is I could have stripped more of the wire casing off. Sorry if it's a little bit blurry. I'm trying to focus it because it doesn't have like an autofocus on the board, but if it's a little blurry, I should be fixing it soon in the video. Now we're going to be taking a look at the capacitors. So this one is an electrolytic capacitors. These ones have polarity, the disc ones don't. We need to be sure to mount them with the negative lead marked on the side in the correct hole. It actually have markings on the PCB that we can follow. So here we just put the 2 leads in, and now we're soldering it. This one is a little bit closer together, so it's a little bit tricky, but this is how you would do it for the capacitors and for the resistors as well. So I'm not going to go too much in depth with it because they are much longer, but this is how I did the capacitors. Again, everything else is very similar, it's very simple. By this point, it's really just practice. I did have a few mess ups that will go into a little bit more depth because the rest of it will be sped up a little bit just to go through time, because everything is basically doing it over again just to get muscle memory. Now the mount IC1, the IC1 was a little bit difficult to mount, and that was just because the leads were very close together, but we'll look at that in a second. So this capacitor, it's done, it looks great. When we're installing these, we need to be very careful because we don't want to bridge 2 solder points together and accidentally short circuit something. If you look at the bottom of the board, we'll pay attention to this a little bit more later, but the bottom of the board has these little traces, and these traces are what's actually connecting each of the different parts together. We went over this before also when we were practicing, when we did not want to bridge. I did accidentally bridge 2 things together, but was easily able to use a solder iron to break that bridge. I turned the light on just so you can see it a little bit better. And now what we're going to be doing is putting the IC1. And the IC1 is going to be mounted. If you noticed, when we put it on the top of the board, there is a little notch and a dot. We need to line those up so that it is inputted into the correct way. If you put it in the wrong way, it could be pretty bad. So we're going to mount the IC1 in the location shown on the diagram that we were given. This is the correct way. We want to make sure the notch or dot on the IC is in the same direction as the marking on the PC board. We can see the drawings. But then we're going to want to solder and cut off excessive leads. However, the leads were actually pretty small, so there is not very much in the way of excess.
Now there is a note here. Do not keep the soldering iron on the IC leads for an extended period of time. We run the risk of overheating the IC, thus damaging it. I believe sometimes I did keep it on for quite a while, so I don't think you have to be extremely careful, but caution is warranted because if you break this, you'd have to order a new part on your own, and that's totally on you, no one else. You can see I am just putting a little bit of solder slowly onto the tip of our iron. That's so we don't get too much solder and we don't have an overflow. This is a great time to actually look at the circuit traces. Notice how everything is going to either connect, or we're using these resistors, these capacitors, our IC1 chip, to connect everything together. We could pull up data sheets for these individual parts if we wanted to look more in depth with them as well. But right here, we are doing this. And actually, so I'm doing a voiceover of the video watching it now, and here is where I made the mistake. You can see that I bridged those two. You don't want that. So what I'm going to do now is use my soldering iron and try to break that away and wipe off the excess on a paper towel. It was very hot, so had to be super careful on that. Did not want to burn myself again because I did twice and it really hurt. So I'm just swiping that away, and it seems like I was able to get them separated. So that is pretty good. That is our IC1 chip on the top, and this is more information about everything here. Looks like there's a little bug and I burnt it. Realize that's not a good idea though, because you want to keep your soldering iron clean. So I will attempt to wipe that off afterwards, but now you can just read over the figures A, B, C, D, and E. We are going to be doing more of figure E and B, the capacitor and resistors. We do have one potentiometer, and we're going to mount that soon as well. I'm going to be clipping off periodically throughout the video a lot of the leads that are coming off the components. You don't want these poking out too much, because if they touch each other, it could short circuit. You don't want that. And on top of that, it just looks a whole lot nicer, and it's easier to deal with. I didn't want to trim them off at first in case if I needed to unsolder something and I needed to move it around if I put it in the wrong location. We've installed the potentiometer. That's the thing that's going to adjust our volume. We are going to install a few other things right now is our little transistors. So the transistors are NPN or PNPs. I don't know exactly which these are. I think they're NPNs based off the actual spec that we're given, 2N3904s. So these have a emitter and collector and a base. Here we're not worried too much about it, but we do want to mount the transistor with the flat side in the same direction as marked on the PC board. It'll give us this direction. We want to leave about 1/8 of an inch space between the transistor and the PC board, and then solder and cut off the excess leads. We're leaving just a little bit of space so that way we can have this above our board. I'm also going to have a jumper wire. I'm going to cut off both ends, and I need to install it on the board in specific locations. We'll see that soon. We also have our LED, light emitting diode. We need 2 of these to be installed flush on the board. These also have polarity. Mount the LED onto the PC board with the flat side of the LED in the same direction as marked on the PC board. Be sure to mount the LED flush with the PC board as shown in our diagram, which I'm just reading out right now, and we've gone over this a little bit previously. It really gives us the direction, which is nice here, but it's important to know that polarity exists with this, kind of same with the transistors and a lot of the other components. Now for the speaker, once we get to that, we want to cut 6-inch wires. They could really be as long as you want, just don't make them too short. And we want to strip about 1/8 of an inch of the insulation off on both ends. We're going to insert the speaker wire through the PC board as shown in the diagram, then insert the wires into the speaker holes and solder each end. We want to solder the other end to the speakers, so 2 wires will go to the speakers, and then the 2 other ends are going to go to the board. Now there's a hole in the board. Remember, you want to solder with the wires going through the top and out the bottom. So we're going to go through the top, out the bottom of the, or we're actually going to go through the bottom, out the top with our 2 wires. It can be a little tight fit, And then we're going to push them through the two smaller holes. Once they're in there, we can solder them together. So we're just about done here. I feel like I should have made these cables a little bit longer, because what I'm going to do next is actually 3D print a little box for this. I'm probably going to desolder these, basically remove these, so it can fit in a nice square box, have this all exposed, but have it kind of recessed in, probably some kind of way I would like slide it in and hold it down to clamp it. And then this would just have its own little spot next to it where it would rest in the whole 3D print. I'll have to go and use my calipers, measure everything, make a CAD for this, and then translate that to the G code to give it to Kira, to give it to my printer. And then of course make some kind of housing where the battery can just slot in. Now, what's cool about this is we have this potentiometer, and this potentiometer, the way it's set up, is it's going to change the volume for this. So we're going to set this battery up in a second. Now the traces here, we can see how everything really connects. It's a little bit hard looking at it first glance, but the circuit schematic that we were given, I can pull it up and we'll go over that again a little bit more in detail because we finished this, and compare it to what we have here. Is basically this. It doesn't look the same, that's okay. Usually it's not going to look the same just because of how everything is laid out, but this is what we got. So what I'm going to do is I'm going to plug our battery in. It's a 9-volt battery. And you can see I can adjust the sound to make it almost non-existent, and then I can also make it louder. And all that's happening is adding more, I think, voltage, or changing the frequency of our wave to go up and down. So that should be changing the voltage. And that is it for this. We've made a really cool project. Hopefully we'll do more in the future and more soldering. This was my first time, so it's a little bit messy, but hopefully I'll get better at it. Now that we have this built, we are going to look at the schematic diagram and compare it to what we have soldered here. So with our schematic diagram, we have all of these lines right here, and these lines are going to represent the traces on the underside of the board. Here on the top side, we don't really see anything, but if we flip it over, we have these tracings all along here, these lines. And these lines are what connects everything together. So let's start on this side. If you've never looked at a schematic before, this is basically just how everything is connected. We have our battery here. It's connected in parallel with this capacitor, connected in parallel with this resistor. This resistor is connected in parallel with our LED and this capacitor. This is connected in parallel, and so on and so forth. And then we have this kind of like bridge right here where we go across, and then this one goes across as well. Now we're going to not look at this entire thing because it's extremely long, and that's not the point of this video, to look at circuit schematics. But let's look at a basic understanding. We know our battery starts right here. So when we flip our board over, that means the two battery terminals are going to be right here. So this left one, or this right one, is going to be our 9-volt power here. And this one is going to be like the negative, the ground. So with that knowledge, our battery is going to go from here, and it's going to go into this capacitor right here. Now, from this capacitor, we can see that these two are connected. So that means when we look at this, when we have our red wire to the capacitor, it should be connected. On the top of the board, it doesn't look like it's connected, but on the bottom, we have this trace right here, and this trace connects the two. Now let's look at another thing. We have this R2, it's 1 kilo ohms. Well, this R2 on our board is all the way over here. But if we look below, we can see that this trace right here, it carries on from over here to all the way over to where our R2 is. And then our R2 should go to this dot right here. This dot's called like a node. And this node is going to split to our C2 and our LED1. So remember, this is our R2 right here, and it's going to go to this side over here. So it's coming out on here. So that means if we look this way, we are going to get our capacitor. If we flip the board over, we have our 10 microfarad capacitor right here. And then this trace is also going to go up to the right, and that's where our LED is. And that's going to work for all of these right here. This symbol right here means ground, so all of these are going to go to this ground right here. And that's how we would look at these traces in more in depth, comparing the actual solder that we've done on this PCB to the circuit schematic. So that is our little comparison. It doesn't look the same. It's never going to look the same because of the layout of the board and how everything works, but that is just the general idea of it and how everything is wired up. We have this quiz that we're going to take. The oscillator in this kit is known as a what? Well, we've talked about this. It's not a one-shot circuit, three-phase circuit, or a tri-state circuit. These are all different kinds of circuit. What we built is a multi-vibrator circuit. Number 2 says what type of flux should be used in electronics. Chloride, organic, rosin, or corrosive. We are going to want to use rosin for the best results. When working on PC boards, what wattage range of iron is ideal? Well, we want something with low watts for PC boards, so it's going to be 15 to 40 watts, typically like 20, 25. Tinning the solder tip will prevent it from heating, melting, soldering, or oxidizing. Well, if we tin it, we're going to keep it from oxidizing, which is what we don't want. Proper solder adhesion requires that the metal surface be what? Solder free, clean, greasy, or cold. Well, our solder surface should be solder free. It should be clean, and it should not be greasy, should not be cold. The solder wick is used to remove solder, solder in smaller parts, cleaning the solder iron tip, or removing the flux. Well, it's not for cleaning the tip because we would use like a towel or something like that with some water to clean it off. We're not going to want to remove any flux. We don't need to do that. What this is for is removing our solder. A cold solder joint is caused by what? This is just insufficient heat. We wait for our solder tip to heat up more, and then we can apply our tin. When two adjacent foils accidentally touch, it is called a what? It's called a solder bridge. We don't want them to touch because it might short circuit something. What ratio has the greatest amount of tin? For the greatest amount of tin is listed first. It's going to be 60 by 40. The frequency of the second oscillator ranges from what? This is specific for our project, and it's from 1500 to 2200 hertz.